Hi everyone, welcome to Flink Forward. In this session, we will be covering Netflix's new stream processing platform, Data Mesh. It is a streaming platform supporting data movement and processing in near real time with a focus on reusability of data and processing patterns. Last year, one of our team members presented the vision behind Data Mesh, and we were building this platform from grounds up at that point of time. Well, last year had been quite productive. Even when as we went through the pandemic and we went to GA general availability last week with over 100 pipelines in production. Today with me, I have A and Andrew, a part of the team that made this possible. In this presentation, we will do a quick review of what were the main problems we tried to solve with Data Mesh and the challenges we tackled and how we address them. Next, we will cover the current status and touch on our future roadmaps. We will be available to take any questions you might have at the end of the presentation. So why Data Mesh? What were the problems we were trying to solve? It all started with trying to find a paved path to move data from operational data stores such as RDS, Cassandra, and CockroachDB to different analytical stores such as Data Warehouse and ES. We have been using batch bulk loads to get this data out, and they were often inefficient and didn't serve the near real-time need of many applications. Thus, we decided to support CDC, change data capture as you know it, as an approach to get the current state of a data store in near real time. Our existing stream processing platform did not support discoverability and reusability organically. This resulted in bespoke, siloed data pipelines with no clear data ownership. As we scale, this became more critical, and we needed a solution to that. As Netflix evolved over the years and stream processing became more popular, we started seeing different user personas who needed to use the platform. Our existing platform was not extensible to support these evolving needs, so users can continue to focus on their business needs, and we can abstract away all the platform-specific details. So definitely, we needed to come back to the basic kind of board and try to redesign our existing platform to solve these things. One of the unique characteristics of Netflix is our lean team structure. So we wanted to be innovative and build an open collaborative platform where other teams can contribute building processing patterns, not just for their team's need, but for broader usage. So we wanted this entire community of the Netflix developers or the Netflix software engineers to be able to contribute to this platform that we are building. We wanted this platform to be pluggable in the sense that it can continue to evolve with our changing needs, because Netflix is growing and we are changing every day. And last but not the least, Netflix is a data-driven company. Data is our first-class citizen. So we wanted to take a look at our existing functionalities that we offer and make data predictable and reliable by adding a bunch of features into this new platform. Now that we have established the why, Wei and Andrew will take it from here and cover the what and the how.
Before building Data Mesh, we went over our existing systems and figured out 5 major challenges which we aim to solve with Data Mesh. First, data is siloed and hard to use. It is even more difficult to track data lineage. The same dataset can be created multiple times with different names, and its processing job can be duplicated. It is a waste of resource as well as making data consumers' life hard. Even though Flink and Kafka are well supported in Netflix, building a stream processing job from scratch is still not a trivial job. Developers usually need to understand the nitty-gritty details of the engine layer to write up the application. Furthermore, it is even more complicated to make the streaming application easy to debug and performant. Depending on the domain expertise of the developer, different streaming jobs can vary significantly in terms of performance and our operational burden. Finally, data can change all the time, and as a result, the downstream job get out of sync when upstream schema evolves. For the next 10 slides, Andrew and I will cover the challenges in more detail. To solve the problem that data is hard to use, track, and audit, we introduce schema to Data Mesh. With schema, free-form data becomes structural. Schema also significantly improves the data discoverability and reusability. All the data change can be tracked and audited. We are also able to expose data lineage as well as data privacy. One of the core concepts in data mesh schema is the producer, topic, and consumer schema. The producer schema is straightforward. It is a schema used to serialize the message. One producer schema can't represent all the messages in the topic. Topic schema is a union schema of all the messages that sends to the same topic. The latest version of the topic schema can be used to represent every message in the topic. This provides a holistic schema for all the consumers that read from the topic. Topic schema usually evolves when the producer schema evolves. Consumer schema, on the other hand, are defined by each consumer to explicitly express all the fields that their job needs. The consumer schema is used for compatibility check, which we will discuss later. Schema is the first-class citizen in data mesh, and schema is defined for every input and output. The data mesh uses a customized version of the Avro schema called iceberg schema. The iceberg schema uses ID-based mapping instead of name-based. The advantage is that iceberg schema can support more sophisticated schema evolution comparing to the Avro schema. The downstream consumer schema is also stored in data mesh system. The consumer schema is used for deserialization, compatibility check, and lineage tracking. Down below is a screenshot of the iceberg source view, which enables open and discoverable data. On the left, it is the schema builder UI with primary key definition, which is a good use for the CS change data capture use case. On the right, all the consumer of the source are listed with its owner and the pipeline links. With this, I will hand over to Andrew, who will cover the next two challenges.
Within data mesh, we needed to ensure that data sets were not duplicated and engineering effort was centralized for similar or overlapping processing logic. Two core building blocks of data mesh solve these challenges. A source or a catalog of sources is made available to end users for consumption. Each source is associated with a schema. Consumption occurs with a processor. A processor is a templated piece of business logic. It's developed once and configured and deployed many times. Multiple processor instances can consume the same source. An example of a processor is a GraphQL enrichment processor, which consumes a message, calls an external GraphQL service, and enriches the message with data from the response before republishing it. Today, there are over 100 sources in the source catalog and several custom processors implemented with Apache Flink. The implementation of a source is simply a key compacted Kafka topic. A special processor called a source connector observes schema and row changes in a data store and emits a corresponding change data capture event in the form of a Kafka message. The message key is set to the row's primary key value, and the message payload is set to the contents of the row. This diagram shows a source connector observing schema and data changes for a MySQL table, specifically from the MySQL bin log. Each type of data store requires a custom implementation for its corresponding source connector, which is why these source connectors are considered special. The key topic only guarantees to maintain the latest message for each key. Therefore, a consumer of the topic, a processor, is only guaranteed to observe the latest state of the table and not necessarily any intermediate states. Processors have inputs and outputs, which are specified by the developer of a processor. A processor has one or more inputs and zero or more outputs. A processor with zero outputs is a sync processor. It produces messages to an external data store. The four processors on the left demonstrate the different shapes that a processor can take. The processor on the top left has one input and one output. The processor on the bottom left has three inputs and one output. The processor on the top right has zero outputs, so it's a sync processor. And the processor on the bottom right has one input and two outputs. Processor developers predetermine fields for end users to configure. Aspects such as field type, field label, description, and optionality are specified. The input fields on the left are displayed to the end user for each processor that needs to be configured. The core building blocks of data mesh leverage Apache Flink and Apache Kafka, two complex technologies that require deep expertise and fine-tuning. Our goal for data mesh is to deliver a simple self-service abstraction for building streaming data pipelines. In order to achieve this, a sophisticated user interface and user experience is needed for configuring them. So what exactly is a pipeline? A pipeline is simply a series of processors connected in a topology. Processors consume messages from the output of upstream processors and produce messages to their own output. This is a simple pipeline. It has one sync processor, which consumes from a source. Easy. This pipeline is a bit more complicated. It has one source, three intermediate processors, and two sync processors. This pipeline demonstrates the capability of data mesh for building complex streaming data pipelines. The possibilities are literally endless. We don't have a live demonstration for the UI, but you can take my word for it. The data mesh self-service UI provides a drag and drop experience for end users to configure pipelines. End users can configure pipeline topology, processor configuration, and individual output schema, all from the UI. No code.
Thanks, Andrew. Only eliminating the duplicated processors is not sufficient. Ensuring every processor is well built is the next challenge that data mesh faces. We embrace collaboration and distributed ownership to solve this challenge. We open up data mesh platform and enable domain experts to contribute their processors to data mesh easily. This ensures the processors are built by the most relevant team, which could be outside of data mesh platform team. With well-implemented and reusable processors, the best practice is applied automatically. We are able to reduce the operational burden. While building the first couple of processors, it is clear to us that every processor would share some common functionalities such as serialization, deserialization, schema-aware processing, and basic metrics. We consolidate those code into the data mesh processor SDK so that the processor developers can leverage them for free. The processor SDK is only one of the offerings in the data mesh processor development ecosystem. To standardize the development lifecycle, data mesh also introduced the default dashboards and alert templates. Furthermore, a Gradle plugin is provided to streamline the processor registration workflow, and a lot of debugging tools are built to simplify the processor development and upgrades. However, each processor is unique by nature. The processor developer needs to implement the processor-specific logics, publishing customized metrics, and generate their own alerts on top of the platform offerings. To tackle the schema out of sync challenge, we built automated schema evolution in data mesh that only requires simple user configurations. With consumer schema, data mesh can achieve flexible and safe schema evolution. Pipelines evolve automatically and recursively. data integrity is guaranteed. No data loss or bad data during the schema evolution process. The first user configuration for schema evolution is to define the consumer schema. The consumer schema is a safety net that ensures an incompatible schema change won't flow into the consuming job unintentionally. Before executing any schema evolution, data mesh platform first checks the compatibility based on consumer schema. We use consumer schema compatibility instead of the forward or backward compatibility because it is more flexible and still accurate. For the same upstream schema change, consumer schema compatibility is checked against each consumer separately. Let's explain this with an example. The upstream source A has 4 fields, and the source is consumed by 2 downstream consumers. Removing the name field would be incompatible for both, since both consume the name field. Removing the episode field would be incompatible for the second consumer, but not the first consumer. Removing the director field is compatible for both consumers, despite that director is a required field. The second pillar of schema evolution is to define a schema evolution configuration is to define the opt-in to schema evolution flag. This is a simple Boolean flag that indicates whether the user's intention is to propagate all fields from the upstream or only the subset of the fields. An opt-in consumer consumes all the upstream fields, including the new fields that added at a later time, while the opt-out consumer only consumed a fixed subset of the fields that is defined by the consumer schema. The opt-out consumers doesn't need to be redeployed for any incompatible compatible changes. That's all the user configuration needed for schema evolution. Here is a screenshot in the data mesh UI, which contains a simple Boolean toggle for opt-in to schema evolution and the checkboxes for consumer schema. Let's walk through the schema evolution workflow to give you a better idea. Evolution starts when an output schema is updated. The data mesh platform fetches all the consumers that of this output and apply evolution workflow against each consumer separately. If the change is incompatible for a consumer, the platform notifies the owner of that consumer. However, incompatible for one consumer won't block schema evolution for other consumers. If the change is compatible, the platform then check if the consumer is opt-in to schema evolution. If opt-out, the platform can safely assume the consuming job can continue running and no need to evolve further. If it is opt-in, all the field will be propagated. The processor will be redeployed with new schema, and schema evolution continues recursively. With all 5 challenges explained, let's summarize what is data mesh. Data mesh is an open, composable stream processing platform which strives to simplify the pipeline building workflow with configuration-driven and drag-and-drop UI. To build a pipeline in data mesh and understanding streaming technology is not a requirement anymore. Besides, data sources in data mesh are discoverable, and the processors are contributed by the expert teams. Both data source and processors are reusable. schema is a for first-class citizen in data mesh, and evolution is fully automated based on user configuration. Data lineage is supported out of the box, and other audit functionality can be supported further. After going through the challenges and concepts in data mesh, we also want to share the current status with some numbers. Data mesh is on GA 2 weeks ago on mid-October 2021, with more than 160 pipelines running in production. 10 processors are contributed by both data mesh platform team and external teams. Data mesh currently supports change data capture events from MySQL, Postgres, and Java clients. On the sync side, Iceberg, Elasticsearch, and Kafka syncs are supported. More than 4,000 schema are registered in production. For future plans, the streaming SQL and transformation processors are the upcoming processor to data mesh, which will significantly improve the capability of data transformation. We also going to add more source connectors and sync processors to streamline the data movement for operational and analytical databases in Netflix. Supporting the logging use case is another major goal, since it is one of the largest use case in Netflix. The ultimate goal of data mesh is to unify all streaming products in Netflix and make it a one-stop shop experience for all end users. That's all for the presentation. If you want to learn more about data mesh, take a look at our blogs and stay tuned for more blogs. We are hiring too. Please let us know if you want to work if you want to work together to build data mesh to the next level. Thanks to everyone for attending. We can take questions from here.